So we'll start to formalize this notion a little bit here. Definition, H71, let F be a finite extension of K. And K bar an algebraic closure. Algebraic closure K that contains F. At the outset, let me try to curtail unnecessary confusion. All algebraic closures of K are isomorphic up to K isomorphism. So that, this may give you the idea that for different field extensions, we make these different algebraic closures, and that's not the case. What is true is any algebraic closure contains an isomorphic copy of F, right? But we're just picking one that actually is an extension of F itself. If sigma I are distinct monomorphisms, sigma monomorphisms from F and K bar, because I mean all of the distinct monomorphisms from F and K bar. And by the way, let me point out that since F is a finite extension of K, it's an algebraic extension of K. And so notice if you have any element of F, it's a root of a polynomial of K. And so you're limited by your number of monomorphisms, right? Because any element of F, can only go finite from many conjugate roots. We define the norm of U and F and I think I'm going to say normal K to be the norm and it's going to be the product of these conjugates. And the trace note that if F is Galois over K, then the norm or product of sum of constants. Let me illustrate what can happen in the non-Galois case. Q and what's the F equal Q going Q root 2. So you're asking yourself how many embeddings from K into the algebraic closure of Q. how many embeddings into the complex numbers. You can think of it that way as well, right? Well, notice that notice that this field, right, a basis for q cube root of 2 over q is 1 cube root of 2 cube root of 4. If you tell your sigma where to take this, then you know everything, because it has to be fixed on q. Once it knows where this goes, then it knows where the square of this goes, because of the fact it's an automorphism. Now it knows where every basis element goes, so we're good to go. So now all you got to ask yourself is this: hey, self, how many places can the cube root of 2 go? Well, it can only go to the other conjugate roots of the images are the roots of right. So you have sigma 1 you have sigma 2 notice that this embedding is actually into Q bar and it's not in the original field, right? It's kicked out. Right, so the norm of the cube root of 2 is the cube root of 2 on omega cube root of 2 times omega bar. Now, let me do one let me do an annoying computation here. What happens to this? Well, the norm of this should be first automorphism, second automorphism, third automorphism, right? And this is kind of obnoxious to multiply out, but I'll go through the trouble. This is 1 plus cube root of 2 plus omega cube root of 2 plus omega cube root of 4. Y'all better watch my best to make sure nothing goes south, further south. And let's see, so this is 1 plus cube root of 2 plus omega cube root of 2 plus omega cube root of 4, and then plus omega bar cube root of 2 plus omega bar cube root of 4 plus omega bar is 1, so that's going to be cube root of 4 plus omega bar is 1, so that's cube root of 8, which is 2.
So is this linear?
Actually, no, the norm isn't, but the trace is.
Okay.
Looks like a mess, right? But notice, let me kind of group things sagaciously. Let's see, I get a 1 and a 2, so I'll call that 3. right? And let's see, where's my cube root of 2 garbage? So notice I've got these three things that are cube root of 2 companions. So I get one, that's the omega bar, cube root of 2. And then I get these companions cube root of 4. You know what these add up to? That's correct. These add up to 0. You know it's 3. And in fact, anybody know why? I'm going to do this just in the Galois case, but it's easy to generalize to the general case here, right? I mean, look at that computation. Not terrible, but it looks like proving this would be just awful, right? But let's suppose that and again, this generalizes. The norm of U is sigma 1 U, sigma 2 U, sigma n U, and UI, the set of UI equals 1 to n is the Galois group of A. Now, notice that for all sigma I of the norm of U is sigma I, sigma 1 U, sigma 2 U, sigma n U. Now, use the fact that sigma I is also an automorphism. Sigma I, sigma 1 U, sigma I, sigma 2 U, up to sigma I, sigma n U. So I could write this way. This is the product of sigma I, sigma j, U, j equals 1 to n. Which is the same thing as that. Can anybody explain that? Notice these sigma i's form a group, don't they? I agree with that. What happens if you have a group G, right? Just spread out all the elements of G, right? Whatever they are, G1, G2, Gn. Now multiply these all by some other element of the group that's already in the list, and you get the set GG1, GG2, Gn. Now, all these little two products are almost the group, right? Is there any duplication? There is no duplication, is there? Because of GGI equals GJ, this implies GI equals GJ. So think about what this means. This is the product over your GGI and GGJs here, which is the same thing as the product over all these. This list is exactly the same as this. So this is the norm of mu. So that means sigma I norm mu is norm mu for all sigma I and gal y. And since it's gal y, this means that mu is in fixed field of the gal y. And again, this can be generalized. There's a similar proof for the trace as well. Any questions? Let me give you some properties of norm and trace. Let F be finite over K. And UV and F. Number one, the norm is multiplicative. And the trace is additive. Number two, U is in K. So suppose you've already got the element U. I know it's an F, but suppose all the way down to the base field, then the norm of U is U to the N, and the trace of U is in U within the degree of and I think I can explain those very quickly. Number three, norm of trace elements K. And in particular, or I'm sorry, if what's the line? Yeah, if f of x to the n plus a n minus 1 u for x a x and 0 is the irreducible polynomial of u from kx, of course. Then the norm is, always get the sign wrong on this one, -1. Is -1 in A0 power F over K. So in particular, if F equals K over U, then this would be -1. Oh, I've got that. Oh, no, that's right. So in particular, if the degree of if KU equals F, then this degree is 1, so you just get that in that particular case. And the trace is minus whatever that degree is, a to the n minus 1. And notice these, of course, are both in K. So in other words, up to a sort of scalar multiple, then what happens is that basically the norm is very closely related to the constant term, and the trace is closely related to this. Let me put one more thing, and I'll do you an example to show where this might come up. For if K and F are fields, then the norm is multiplicative. U is equal to norm F. And the trace imposed is the trace. Okay, okay, so let me go through at least a brief explanation of some of this. So let's just think, yes.
On number 3, you just said it is irreducible polynomial. Is this specifically like the middle polynomial of U, or just any irreducible polynomial of which that is?
The irreducible polynomial will be the minimal polynomial.
Got it.
Yeah. So, for example, if you look at the norm, well, no, it actually doesn't matter. Norm And the proof that the trace works this way is similar. If right. Right. Where these are the embeddings from F into complex numbers, and there's exactly N of them. And so this is the product. Because since U is in K, it's fixed by all those things. And so this is again, proof of the trace is very similar. For I'll let you work out 4. It's not too difficult to just show that it composes the way you hope it composes. Let me give you an example here to illustrate 3. So actually, I can illustrate 3 and 4 this way. So let's let for omega the 2 pi I. So this is again the primitive cube root unity. I can refer you back to earlier notes where we wrote an explicit table down for the automorphisms of that big field. I remember when we went through all that. Notice that the norm we just did that. Right. Now, what is the norm? So let's test this a couple of ways. Well, notice that notice that actually F is a Galois extension of K and hence V. Right? Now, how many embeddings are there that fix? How many embeddings of this F are there in the complex numbers that fix? So you're supposed to fix cube root 2, right? There's only 2 of them. It's complex conjugation. Or alternatively, you could take omega 2 omega bar, right? So there's 2 embeddings, and this should be notice both of these embeddings fix this. Right. Actually, I didn't want to start there on the last word. That's fine. Go ahead. Okay. What is this? This is also 2 times 2. Now, this is sort of why number 3 works. Notice how many embeddings are there? How many embeddings are there from here to the complex numbers? Well, this is the same as, remember, this extension is Galois of the cube. So how many automorphisms does the big field have? Anybody remember what the Galois group of the big one is? Q adjoined with the cube root of 2 and omega. Anybody remember that?
Was it S3?
It was S3, that's right. So let's see what happens when you do the norm here. So if you look at the norm, you pay the F, cube root 2. Well, let me try to talk through. Notice there's 6 of these, right? So, okay, let's see, what can we do here? The first one, identity, right? Second one, complex conjugation. Agreed? So there's 2 of them that do that. Third one, there's an embedding that takes this to that. Right? And compose it with complex conjugation. And you get another one like that. There's also, right, because that even conjugates, it doesn't. Well, if you look at the table, there are certainly 2 embeddings that take this here, and there's 2 embeddings that take this here. If you refer back to your notes, we did all that. So if you look at where there's 2 embeddings, namely identity and complex conjugation that leave this alone, there's 2 embeddings that take it to this root and 2 here. And if you multiply this big mess together, omega bar is 1, omega bar is 1, so that's gone. So basically what you get is the cube root of 2 to the 6th power, which is 4. Right? Everybody okay with that? So that's what the norm is with respect to this field. Now let's notice a couple of things. Notice that the norm this should be the norm. Let's see, we figured what this one was. This was actually the norm from E to K of, actually we need F to E at cube root 2. This is 2 to the 2/3. And this, of course, is cube root 4. And when you do the norm of this, this is basically the norm E to K is the 3 places you could send the cube root 4, which is the cube root of 4, omega cube root of 4, and omega bar cube root of 4, which is 4. So we got a match. And the minimum polynomial for cube root 2 over Q is x cubed minus 2. And let's see if we can get a match here. In this case, F is cube root of 2 omega, and degree of F cube root of 2 is 2. Right. So what the norm from that perspective is minus 1 to the 3 power -2 all squared. So any questions on that? Okay, so we're building up to like a theorem, very famous theorem of Hilbert and his companion for the trace. Just out of curiosity, how many of you have ever heard of Hilbert's theorem 90? Have ever heard of that? I guess that means Hilbert had a lot of theorems. It's important in doing things like group cohomology, things like this. But first I need to tell you something. Definition. Here I'm going to let S be any non-empty set of automorphisms of the field F. Else non-empty set of automorphisms we call the set linearly independent. Say S independent given any collection right, any collection AI of elements of F and sigma I and S, then the relation AI sigma IU is equal to 0 for all U and F implies that AI 0. So what it means for these set of automorphisms to be linearly independent is that if there's so basically what this means is this linear combination of these automorphisms is identical to 0, right? Because this sum of AI sigma I acting on any U and F always gives you 0. If this means that all the AIs are 0, then we say that this is a linearly independent set of automorphisms. So let me give you a lemma that almost renders this definition useless. Basically, if you have any distinct set of automorphisms, it's linearly. If S is a set of distinct automorphisms, then S is linear. Okay, so let's go through a proof of this. This is really kind of pretty. I love this proof. So if not, you can find non-zero AI and distinct sigma i's so that these AIs, not all zero. And distinct sigma i's such that I'm gonna write this out explicitly. A1 sigma 1 u plus A2 sigma 2 u plus A1 sigma 0, and this must hold for all u in F. Assume this relation of dependence is minimal. Right? And see, this is kind of the trick that makes me think I know it's going to work, because there must be some minimal dependence relation, right? Because, and that n has to be bigger than 1. Because if I have A1, if I just have 1, if I have A sigma of u is 0 for everything, remember, sigma is an automorphism. So if A is not 0, that means that sigma is killing everything in u. There's no way it's an automorphism, right? Because it's 8 1 to 1. So assume that n is minimal in this sense. So this is the smallest dependence relation. Since automorphisms are distinct, we can find some V and F such that sigma 1 of V is not equal to sigma 2. So let's apply this dependence relation equation to what we have here. So let's note that A1, sigma 1 UV, it's A2, sigma 2 UV, AN, sigma N UV equals 0, because that dependence relation has to show for, has to hold for anything in F. In particular, it holds for UV as well. And so let me write this out. And now multiply, let me call it star here. Star sigma 1b to obtain A1 sigma 1b or sigma 1u sigma 1b A2 sigma 2u sigma 1b AN sigma NU sigma 1b 0. And so if I subtract second from first, what I get is, so if I subtract this minus this, of course, this is dead right here. Right? And this is A2 sigma 2U sigma 2B sigma 1B plus AN sigma NU times sigma NB zero. Agreed? Now, let me point out something. Notice that the difference here, because of the fact this is an automorphism, this is still in the field, and so it can be pulled up here, right? And notice that this one right here is not zero, right? Because I assume that sigma 1b and sigma 2b are different. And so this means my dependence relation is now smaller. So they're linearly independent. Now let me make a quick correction in the proof. Actually, I meant for these, not all zero, all not zero. So I will admit any ones that have the zero AI. Okay, any questions on that? Any questions out there? All right, well, are there any questions? Y'all have a good one, and we will see you by Wednesday.